talk about Unit K.3, Forces in Motion. Joining me today is Danny Hewells, who's the Curriculum Development Specialist at Michigan State University and also the lead of this unit. I'm Janita Vasquez. I'm the Elementary Curriculum Manager here at OpenSciEd. Thank you for joining us. So just a little bit about what this recording is about. We're going to talk about OpenSciEd Elementary. In case you're not familiar with our materials, we are going to walk through the first lesson. Danny's going to help us do that. She's also going to give us a tour of the unit storyline, show us some key features of the unit, some stuff that she's really excited about, and then we're going to talk to you about some additional resources that we have for you on our website. So very quickly, OpenSciEd is an innovative nonprofit organization that brings together amazing curriculum developers, state science supervisors, teachers, and philanthropic organizations. And they help us develop high quality, free, easily accessible on the internet instructional materials and professional learning aligned to those materials. In case you don't know, we field tested these units with 9 partner states with over 450 teachers, and those teachers helped us get data from around 10,000 students. So lots of folks lent us their voices to help us make these units as wonderful as we could make them. So a little bit about our OpenSciEd materials. First, we follow a storyline model for development that starts with an anchoring phenomenon, has investigations, lessons, putting the pieces together lessons, and navigation from each. And Danny's going to talk to us more about this model. We, again, build on a storyline model. We really want to engage students in asking questions about phenomena, things around them, and using those questions to drive the unit learning. Lessons in the unit are always connected and in the service of making sense of whatever the phenomenon is that we're trying to answer through lots of investigations and research. As you can see, we have 4 units in each of our grade levels, and our units are designed with a recommended sequence, but they are also built to allow for flexibility and modularity. So you can decide how they best fit into your school year and your school context. So just a little bit about the nitty-gritty of our units. In K2, today we're talking about kindergarten. Again, there's 4 units per grade level. In each of those grades, there's 10 lessons per unit. Those lessons are 60 minutes in length, but in OpenSciEd, when we say a lesson, we don't say one shot, one day. We mean 60 minutes that can be scheduled flexibly throughout your week or across weeks, if that's necessary in your school schedule. That adds to 2,400 minutes per school year, or about 4.5% of your full instructional time. That makes OpenSciEd totally doable and achievable in your school classroom, along with all your other expectations as an elementary teacher. In grades 3 to 5, just very quickly, we have up to 15 lessons per unit, and we say that because some of our units only have 12 lessons, 12 to 15 lessons. Each of those lessons is 90 minutes in length, again, meant to be flexibly scheduled within your school day or week, and that will add up to 5,400 minutes a school year, or about 10% of your instructional time. One of the things that's important to us in OpenSciEd is to integrate both math and ELA. In math, we really think about integrating mathematics in the service of understanding and making sense of the science that we're learning. We integrate math through math talk, modeling, and thinking about data concepts, but data is where we spend most of our time. Our students starting in kindergarten are planning to collect data, analyze data. It's really important to us for students to understand those concepts. And also, we really think about supporting literacy for all of our students. We have designed a collection of student books and other artifacts to really think about literacy. We focus only on informational text so that that can complement your other ELA instruction. We think vocabulary is very important, but we like to integrate it in the context of learning the science. And we focus on communication, whether it be oral, in writing, using gestures. We really want our students to be able to communicate their learning in lots of different ways. And we also offer you a comprehensive assessment system. So we don't only offer you all these different types of assessments, but we support you by providing rubrics, support with next steps, scaffold for students. What do you do in instruction after you collect all this assessment data? So that's something that we do throughout our program. And finally, if you're interested in our materials, you can go to our website. And while you can find our materials free and easily accessible on our website, you can also purchase kits and printed materials from our vendor partners. And you can find that on our site. All right, so that's it for me. And now we're going to get to know Unit K.3, Forces in Motion. And Danny is going to take over and tell us all about this great unit.
Thank you. Once again, I'm Danny Hills, the unit lead for K.3, and I'm so excited to share this unit with you. I'll be walking us through the kindergarten physical science unit, K.3. The overall unit is how can we move things to where we want them to go? This unit focuses on motion, forces, and engineering through the lens of pushing and pulling objects. This unit is the 10 lessons, about 60 minutes each, and blends hands-on investigation, sense-making, and engineering design. By the end of the unit, students not only understand how objects move, but they also apply that knowledge to an engineering game that uses pushes to move a ball along a path to the ending point. So as we walk through the K.3 unit, we will highlight how each part of the OpenSciEd instructional model is used to support student sense making. So this model follows a pathway that begins with an anchoring phenomenon, followed by investigation lessons where students gather evidence to figure things out. About midway through, there's a putting the pieces together opportunity to help students synthesize what they have learned so far. Students then engage in additional investigations to deepen their understanding before ending the unit with a final putting the pieces together lesson where they make sense of everything they figured out, including applying it to their engineering design. First, I'm going to begin by introducing you to the unit by spending a little bit more time talking through the anchoring phenomenon lesson. So in all OpenSciEd units, the first lesson serves several important purposes. It introduces an interesting phenomenon or problem to spark curiosity. It gives students an opportunity to share their initial ideas. It motivates students to ask questions that they will investigate throughout the unit. And it also serves as a pre-assessment opportunity for the teacher to learn what students already know or wonder about, which will get that student-driven unit. All right, so let's dig into the first lesson. So to launch the unit, students are presented with a relatable and concrete challenge, moving too many objects at once. So the teacher sets up a scientist circle and places around 20 objects, school supplies, far more than a kindergartner can carry on the table or floor. Then one student is asked to try holding them, all while classmates pile objects into their hands. So it doesn't take long before students experience the struggle. From there, the teacher facilitates a discussion using prompts like, have you ever had to carry it a lot of things at once? What happens when we try to hold everything? Can you think of ways to move all these things together? And what I love about this moment is how quickly the kindergartners bring in their lived experiences. They hug the objects, stack them all up, call for help, pretend to use a backpack or a shirt. You start to hear the early seeds of engineering ideas begin to emerge naturally. So, this experience sets the stage for co constructing the lesson question with the students. So, based on their suggestion, the teacher moves all the objects into a box, and then the box is too heavy to pick up. So students help co-construct the question like, how can we move things from one place to another? So after developing the lesson questions, students begin a hands-on investigation by exploring different ways to move a box filled with objects. So first, the teacher demonstrates how to record observations on the handout and reminds students that observations mean looking closely to understand what is happening. So students work in pairs. Each pair gets a box with their about 10 objects, and each student gets their handout to record their ideas. Every student has an opportunity to make observations and record. So as students explore, the teacher uses prompts to support student thinking. These prompts help students make sense of what they're doing and connecting the way objects move to the forces they apply, while also using the cross-cutting concepts of patterns. So once students have explored and recorded, the next part of the lesson brings the class back together to compare what they observed. So then the students gather in a scientist circle with their completed handouts to share their initial ideas about how we can move objects from one place to another. So in OpenSciEd, we often use the scientist circle to support students in hearing and seeing one another during important discussion moments. So that scientist circle provides an opportunity for students to discuss what they noticed and wondered. So the notice and wonder chart is used to keep track of thinking and questions throughout the entire unit. The teacher facilitates a class discussion and adds any student ideas and questions to the chart using both words and even simple drawings. Students share how they move the box and begin to ask questions that will guide further investigations. This sets up that storyline instructional model. This discussion also serves as a pre-assessment opportunity. So finally, the word motion, after this discussion, the word motion is added to the word wall. This helps students connect their own experiences to the science vocabulary in a meaningful way. So in OpenSciEd, we don't pre-teach vocabulary. Instead, students build language through experience. So the curriculum focuses first on developing conceptual understanding through investigation, reading, and communication. Only after the students have made sense of an idea do we introduce the word used to name it. So like in this example, students have been talking about how something moved. The teacher helps connect their thinking by saying that when we talk about something moving, we're talking about an object in motion. So students are asked if they've heard the word motion before and what they think it means. So building on their ideas, the teacher explains that motion means moving from one place to another, and then that word is added to the word wall. Then, to help students connect the challenge of moving a box to everyday experiences, we begin by having them think about games played in their neighborhood or community. So students often respond with places like the park or gym and games like soccer, basketball, or bowling. Then the newsletter is introduced. The carnival is back at Jacobson. The newsletter is about a family carnival at a school. There are 3 games highlighted: tug of war, bottle bowling, and mini golf. So when reading, students are asked about the motion involved in these games. Next, students watch short videos of the carnival games. So sometimes it's hard to figure out how something moves just from pictures. So these videos will help students observe motion more clearly. This also gives an opportunity for students who may not have had that firsthand experience with these games to make observations of how motion is important in each game. So in tug of war, students focus on how the rope moves and what happens when players pull with different strengths. Then in bottle bowling, students observe how the ball moves and how it causes the pins to move. They can begin to describe the interaction of collisions between the ball and the objects it hits. They may also notice the speed of the ball and effect it has on the pins, or observe how the direction of the ball could result in no collision at all, which the first few times of trying to hit those pins, it was not as easy as we thought it would be. And lastly, we have the mini golf. So in mini golf, students watch how the golf ball moves toward the hole, including changes in direction and speed based on how it is pushed or hit. They may also observe how the ball changes direction when it bounces off the sides or other objects, or how it misses the target completely. So after reading about the games and watching the videos, students now have enough shared experiences to have a meaningful discussion with their peers about the motion involved in each game. So each game has an image to represent it, and it's placed around the room. And then the students rotate in small groups to each image to discuss how objects move in the game and what might make the games challenging. After the small group discussions about the games, it's time to come back together as a class for another scientist circle moment to share any new ideas and questions. This is another pre-assessment opportunity, and these discussions begin to surface key science ideas about like the direction, collision, speed, and the strength of a push or pull that will drive the unit. So after gathering all ideas and questions, the teacher helps students see that many of their questions are really about solving a problem, how to move something to a certain place. So the teacher proposes the unit question, how can we move things to where we want them to go? So this becomes the focus for the next few weeks during science time. The unit question is added to the top of the notice and wonder chart to guide investigations throughout the unit. The teacher displays the class notice and wonder chart, but then notices there we can organize our ideas and questions so that similar ones can go together. So this step helps students start to notice patterns in their thinking and supports the class in figuring out what they might want to investigate next. At this point, the teacher only uses the language that the students have shared. The discussion reflects the ideas generated by the class, often about direction, speed, turning, or stopping. And this discussion helps wrap up that anchoring phenomenon lesson and launches the storyline that will drive the rest of the unit. So to recap, in lesson 1, students make observations about how to move objects using a box and share their observation questions on that notice and wonder chart. They read a newsletter, that article about a community carnival where moving objects was a challenge in the games. They watch the videos of the games in action and discuss the motion and challenges involved. Then they come together to add any new notices and wonders to the chart that can be investigated further. So in this lesson, students figure out that pushes and pulls can make an object move. Now they're wondering which direction objects move when they are pushed and pulled. So before moving into the rest of the unit, I want to take a moment to highlight how navigation works across lessons. This is an integral part of the storyline instructional model. It's deciding together between steps of what we need to do next, so the unit is coherent from a student's perspective. So this class has shared a mission to figure things out, and the sequence of work in the unit helps them make progress on answering their questions. So if someone were to come in and ask a student, why are you doing this today? They should be able to connect it back to their own questions about the phenomenon. We're trying to figure out how we can move things to where we want them to go, rather than just, my teacher said this, and this is what we're doing today. So let's tour the rest of this unit by lesson type. and see how the lessons are connected. Most of the lessons in a storyline unit are investigation lessons. This is where students engage in science and engineering practices. They collaborate to create a plan of action. Um, the teacher provides students with a space to grapple with and figure out and make sense of those science ideas. So the instructional model graphic here on the slide, it follows a fifth grade unit where investigations involve measuring plant growth, investigating insects, and reading with partners as a whole class. So let's see how investigation lessons play out in the K.3 unit. In lesson 2, students begin investigating the direction something moves when it's being pushed and pulled. They read about how to plan an investigation, and then work together to plan and carry out an investigation to figure out which direction objects move when using pushes and pulls. So through this, students figure out that pushes move something further away and pulls move things closer to us. They also begin to understand that they can plan and conduct investigations to explain how and why things move. Now students are wondering what other effects pushes and pulls can have on objects. In lesson 3, students use toy cars to investigate how pushes and pulls of different strengths affect motion. They use the planning and carrying out investigation cards to plan and conduct the investigation. Then the class gathers and analyzes data to figure out how the strength of a push or pull changes how fast and how far an object moves. So students figure out that a big push and pull causes objects to move faster and further, while small pushes and pulls cause objects to move slower and shorter distances. So now students are wondering how to make objects move in other ways. And I want to note on this slide that the chart that's shown is just for pushes. There is a chart for pulls. It's just not shown, but it is similar and used in the same way during an instruction. So in lesson 4, students use toy cars to investigate what happens when objects collide. They plan and carry out an investigation and use what they observe to argue from evidence about how motion changes during collisions. So students figure out that when an object collides with another object, it can change direction, slow down or stop, push on the other object and make it move, change the motion of both objects involved. They also read a book that shows how people around the world use pushes and pulls in everyday life, helping students connect that science ideas to real experiences. So now students are wondering if it is the same with a different object. So before moving on to lesson 5, I want to point out that there are important moments in the unit where students put the pieces together. So these putting the pieces together lessons give students the chance to connect ideas that they have figured out across multiple lessons and apply those ideas to the unit phenomenon. So it's also a place or a time for students to take stock of their learning and work together to develop a fuller explanation of what they're figuring out. So the unit feels coherent and meaningful from their point of view. So in lesson 5, students use a ball to investigate how pushes and pulls can change its motion. This is the putting the pieces together lesson where students plan and carry out investigations by pushing and pulling the ball. They observe how it moves and what happens when it collides with materials like straws. They also share their own experiences with pushes and pulls from home and read about how people around the world use them in their daily lives. The students figure out that a small push or pull causes the ball to move slowly and stay near. A big push or pull causes a ball to move fast and far. When the ball collides with the straws, its motion changes, and there are many objects we move using pushes and pulls. So now students are wondering how we can use what we figured out to design a game. The teacher helps motivate the shift because it does seem like a big shift. But within that notice and wonder chart, at some point, most notice and wonder charts will have that idea of creating their own game from the article. So these ideas will spark the beginning of that class engineering challenge, which is so fun and engaging and such a great opportunity for students to apply what they have figured out with the science ideas and apply that to the engineering problem. So we are back to the instructional model to highlight that lesson 6 is a re-anchor opportunity for the unit. Students are transitioning from figuring out how objects move to applying that understanding to design a game. So just like in that first lesson, this moment includes an interesting challenge or problem to launch that next part of the storyline, a chance for students to share their initial ideas, motivations for students to ask new questions and begin the engineering work. And this is also another pre-assessment opportunity for the teacher to learn what students already know and are ready to figure out next. So this re-anchor keeps the unit coherent from that student perspective and sets up the next round of investigations and design work. 6, students begin the engineering design process by defining the problem, how to design a game that uses pushes or pulls to move an object in the classroom. They read a book to learn how engineers identify problems and create solutions. Then they make observations about mini golf games to help them think about what is needed for the games that they will design. So the class creates a gotta have it checklist to capture the key needs for their games, which they will use throughout that engineering process. So they figure out engineers, identify and solve problems, and ideas from existing games can be used to make new games. So now students are wondering how they can design a game to create their own game. And this is a return to the instructional model. As a reminder, we're returning back to those investigation lessons. So after re-anchoring in lesson 6, students now investigate to figure out how they can build a game using what they figured out in those previous lessons. So these lessons continue to give students opportunities to engage in science and engineering practices, collaborate to create a plan of action, and make sense of science ideas through that hands-on exploration and discussion. So in lesson 7, students begin planning how they might design their own game boards. They reflect on what they have figured out so far about motion, including pushes and pulls, direction, speed, and collisions. They sketch out game ideas, think about how objects will move during the game, and consider how intentional collisions might be part of the challenge, like creating a path for the ball to collide with to get to the ending point or to change directions around an obstacle. So this is where the science ideas start to come together and turning into an engineering plan. So now students are wondering if they can start building their their game board designs. So in this investigation lesson, lesson 8, students build their game board designs. They read a book to learn how engineers use their plans to guide the building process. Then with a partner, they use their design plans to construct their games. So by the end of the lesson, they decide they are ready to test their game boards. So they figure out engineers use plans to build designs, and they can use their plans to build their own games. So now they're wondering if their game board designs work as intended. In lesson 9, students test their game board designs. They begin by reading a book to learn how and why engineers test their designs. So then with a partner, they test their games, analyze how well they work, and make any needed changes. So by the end, they decided they are ready to share their design solutions. Students figure out engineers test designs to see if they work, and they test their own designs to see if they work as intended. Now students are wondering how they can communicate their design solutions to others. And we are back to the instructional model again to highlight that lesson 10 is a putting the pieces together moment. So once again, in these lessons, they connect what they figured out across multiple lessons, apply their ideas to the unit phenomenon. So it's a time for students to take stock of the learning and work together to develop a stronger explanation for the unit question, how can we move things to where we want them to go? In lesson 10, the putting the pieces together lesson, students begin by reading a book about how engineers communicate their design solution. This helps them think about the importance of explaining how their designs work and why they made certain choices. Then students share how their final game board designs work as intended. They draw their game designs and use them along with that gotta have it checklist as evidence when sharing. So students use the checklist to explain how their designs meet the needs identified earlier in the unit. They also compare their solutions to see how different designs solve the problem of needing the game to play in the classroom. And they figure out, engineers share their design solutions with others to compare how they work. Their observations and design choices can be used as evidence to share how their games work. And sharing and comparing their designs help determine how different solutions work to solve a problem. And that wraps up the K.3 unit overview, where students go from figuring out how things move to designing their own game using those ideas. So I have a few key features of the unit I'd like to point out as we wrap up the overview. So the first key feature is a student-designed ball game, which is an engineering focused while also using science ideas. Students go through a full engineering design process to create their own game that uses pushes to move a ball along a path. They design, build, test, and revise using materials and ideas from earlier investigations, building both creativity and problem-solving skills along the way. Feature is the hands-on investigations of force and motion. Students conduct repeated push and pull investigations using toy cars, a ball, and other materials to explore how the strength, collisions, and direction of pushes and pulls affect how objects move. These experiences build foundational ideas about cause and effect in physical science. And the last key feature is the planning and carrying out investigations. So throughout the unit, students work together to plan and carry out investigations using tools like the planning and carrying out investigations cards. So these supports help guide their thinking as they decide what to test and how to collect useful observations. This process builds their ability to ask questions, test ideas, and discuss results with others. So let's take a look at the standards that this unit addresses. And these are the key performance expectations for forces in motion that guide the learning throughout the unit. So we have the physical science performance expectations are the KPS21, which is plan and conduct an investigation to compare the effects of different strengths or different directions of pushes and pulls on the motion of an object. And then the second one is KPS22, which is analyze data to determine if a design solution works as intended to change the speed or direction of an object with a push or pull. And then we have the K2 engineering standards, which is ETS 1.1, ask questions, make observations, and gather information about a situation people want to change to define a simple problem that can be solved through the development of a new or improved object or tool. ETS 1.2, develop a simple sketch, drawing, or physical model to illustrate how the shape of an object helps its function as needed to solve a given problem. And then ETS 1.3, analyze data from tests of two objects designed to solve the same problem to compare the strengths and weaknesses of how each performs. So while students engage in many practices throughout the unit, two are intentionally developed and progress across lessons. We have planning and carrying out investigations and analyzing and interpreting data. So these practices are built into multiple lessons to help students get better at thinking and working like scientists and engineers. Other practices show up too, but these two are the clear focus throughout the unit. So, like the science and engineering practices, students engage with many cross-cutting concepts in the unit, but two are intentionally developed across the lesson. We have patterns and cause and effect. So, these concepts help students make sense of how and why things move, while others are present. These two are built in across the unit to deepen their understanding.
So, Danny, I have one question about this unit because I noticed that we did something that didn't happen during Unit 1 or Unit 2, and that is that you re-anchored. You went back and did a re-anchoring lesson for this unit. Can you explain why the team chose to do that?
We thought it was important to re-anchor because the students will be asking about if they could design a game like they saw in lesson one, that is motivated from the discussions that they have in lesson one. Um, However, we re-anchored to pull that question, but then dig deeper to get those engineering questions. Like, how can we design it? What do we need to do? So we needed more questions to drive that last half of that unit, to make sure there was that student coherence there.
Got it. Thank you so much for explaining
You're
that.
welcome.
And everyone, we just want to talk to you about a couple of additional resources that we've added on our website. If you want to think about upcoming professional learning opportunities, you can go to our website and do that. Also, we just opened our Facebook groups to the general public. So if you as a kindergarten teacher would like to go and join our Facebook group community, please do that. That way you have a full community of writers, teachers, facilitators to chat with about these units and ask questions and help each other. And also, if you'd like to see other webinars and find some other resources, you can go to our on-demand page, which is here also on this slide. I want to thank Danny for being here with us and giving us such a thorough explanation of this unit. I can't wait for everyone to try it in their classrooms.